Welcome to Chapter 3, Section 2, the derivative. And in this section, we're going to continue to look at the slope of a tangent line, but we're going to define it a little differently, and we're going to call it by another name. So in this first section, we looked at the slope of the tangent line can be written as a slope function called f prime, and that is simply equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. And so we've defined this as the slope function. We can find the slope, all that. This is still going to remain the same, but now we're going to call this a little different. We're going to say that f prime of x is the derivative of f with respect to x. So we've taken the derivative of f with respect to our variable x, and that's what we get. That function, that slope function, gives us the first derivative. Now, there's two ways to define a derivative. We can look at it geometrically, and that's the slope of f at x. And so when we graph the derivative, that gives us the slope of our original function f for every given x value. The other way we can look at it is the instantaneous rate of change of y equals f of x at x. So the function y equals f of x, its instantaneous rate of change at every x value is f prime of x. And so when we graph f prime of x, when we state f prime of x, whenever we use it, it gives us these two things, which are kind of one and the same, but they're two different aspects of what the derivative of a function really is. Now, there's a few different notations that we're going to use in this course, and the first one is this D notation. All right, now this is a script D, and we have a ratio here, but I don't want you to view it as a ratio. Later on in the course, we're going to define what is dy and what is dx and what those specifically mean. Right now, we're just looking at dy dx as one quantity, or df of x dx as one quantity. And what that quantity means is it means take the derivative of f of x with respect to x, and that gives us f prime. And so when you see dy dx, assuming that this is the case where y is equal to f of x, all right, in this case, well then dy dx is still simply f prime of x. So this is a notation that we're going to use, the d dx, and we say it that way, d dx of f of x, or df of x dx, that gives us f prime. It just tells us we're taking the derivative. Same thing with dy dx. That's just taking the derivative of y, and in this case, if y is equal to f of x, it's f prime of x. Another way we could write this is if we want to evaluate at a specific point, we're going to have the same D notation, except we're going to have this vertical line here with x equal to x0, or this could be x equal to 3, or x equal to 7, or x equal to whatever number you want. It just simply means evaluate your derivative at that x value. So if you see the df of x dx evaluated at x equals 2, you're just putting in 2 into your f prime function. Same thing with dy dx at x equal to 6, well, you're just putting 6 into your f prime function. Okay, well, now that we have the notation, let's talk about where derivatives are not defined. And derivatives aren't defined at three major areas. They're at corners, vertical tangents, and points of discontinuity. And we're going to look at graphs of each of these and prove to ourselves that the derivatives aren't defined. We just don't have a defined derivative at these three spots. So let's look at a graph that has a corner first. And right here we have a corner at that spot. And notice, go back to when we first talked about the slope of our tangent line. That's simply the limit of the slope of the secant line. So as the 2 points of a secant line get closer and closer together, and as that distance between those 2 points, these two x points, come to 0, that gives us our tangent line. So we can approximate our tangent line by creating several secant lines in succession to see what is our tangent. So if we come from the left, we draw a secant from here to our point, which is at the corner, and we keep drawing secant lines at points closer and closer and closer and closer to that point until we arrive at a tangent line that has this positive slope. Well, if we do the same thing from the other side, as we get closer and closer and closer, we see that we have a tangent line with a negative slope. Well, obviously, we can't have two conflicting tangent lines at this corner, so therefore the derivative is undefined, or the derivative f prime of x at this point, say this is, we'll call this x1, so f prime of x1 does not exist. So let's look at the other situation where we have a vertical tangent. So this is a curve, it's a function. We have a vertical tangent right here, and we can confirm that by seeing that as we look at our secant lines from the left, we get closer and closer and closer to a vertical line. And as we look at our secant lines from the right, we get closer and closer to the vertical line. And you might ask, well, wait a minute, why isn't the tangent line there just a vertical line with infinite slope, so why isn't the derivative infinite? Well, here's why. If you look at these limits, over here we're approaching positive infinity, but over here we're approaching negative infinity. And so if we approach two different areas, and why is this positive? Well, this is a positive slope that's getting bigger and bigger and bigger until it's infinite, and this is a slope that's negative that's getting more and more negative until it's infinitely negative. And so if you look at a limit from the left and the right, and they're not the same, then this limit does not exist at that point. Therefore, the derivative at that point does not exist. And we can look at the third option here of a discontinuous point, and use the same reasoning to see that, okay, here's a point of discontinuity in our function, and as we approach from this point on the left, we get a vertical tangent. As we approach from this point on the right, we get a horizontal tangent. Obviously, those don't work, so this limit does not exist. Okay, so here's a theorem. Theorem 3.2.2 states that if f is differentiable, meaning that the derivative exists, f prime of x is defined. Okay, so if we have f is differentiable at a point x0, then f is also continuous at that point f0. So this tells us that if f is differentiable, meaning that if we can find the derivative at any given point for any given x, then it's continuous. So if a function is differentiable over all values of x, then that function has to be continuous for all values of x.